Hello, everyone. This is Group 21, and I'm Soumya, and we have Jimmy and Akash with us. So today we are going to discuss about incentive mechanism design for unbiased federated learning with randomized client participation. So our agenda includes overview of the paper. We are also going to discuss about some key concepts about the paper. We're going to give a brief overview of existing solution and the problems. Then we are going to dive deep into the proposed design. We are going to explain that. And we are going to conclude with observations and results and our personal opinions about the paper. So most important concept about the paper is federated learning. Federated learning in simple terms is training a machine learning model collaboratively. So you'll have a global model and local model on your devices. Um, the local model is basically a machine learning model that exists in your mobile, laptop, or any kind of edge devices. And the global model stays in the server uh, that is provided by some cloud service provider or some other company. Uh, Federated learning is very important in present scenario because we can see it in our day-to-day basis with, say, for example, text messaging and autocorrect and next word prediction. And also in the security domain, for each and every antivirus system, we have a global antivirus model and a local antivirus model in your laptops. This provides better data security and also prevents us from data breaches. Uh, this gives us more access to better machine learning model. This is a detailed explanation of federated learning. So for example, one antivirus company has a global model. We can see it in the gray box. And there are different people staying in different countries. Uh, So at day zero, they wanted to access the global model, and the global model has generic checkpoint of all kinds of malwares. So they can defend their systems with that. Now, for example, a Trojan from Taiwan gets mixed with spyware in India. So India has spyware plus Trojan from Taiwan now. So India queries the global model and sees if there is any checkpoint for Trojan or not, and defends their system. But the malware evolves with time. So India would have a different kind of Trojan after, say, 6 months. Now, uh, the local models in India gets trained with the new variant of Trojan, and that is sent back to the global model. Similar thing happens with all of the other countries. So in this way, we have all protection towards all kinds of malware stored inside a global model, which is a very powerful model. And whenever some country needs some kind of protection towards a malware, it can query, and vice versa. The model gets updated in a local system, and also it gets updated in the global settings. Another important topic is incentive mechanism. So the clients are supposed to train the model in their local devices, but they need to incentivize. Otherwise, why would anyone ever do it? So normally the cloud service provider gives you incentivizes you by services, monetary compensation, or some decision power. We have listed bunch of other mechanisms too here. Um, The third important point is client participation. So we need to know about full client participation and partial client participation. So towards the global training objective, sometimes during the entire training time, there's a fixed subset of clients that participates towards the training. That is partial client participation. And sometimes the cloud service provider asks that all of the clients participates for the training, then that is full client participation. Normally, the existing solution focuses towards creating a deterministic subset of clients and training with them. So this is the deterministic or existing approach. This is mainly based on the client's computation power, data quantity, or communication bandwidth. So we can see in India, say for example, Soumya has greater resources. In Taiwan, Jimmy has greater resources, and in US, Akash has greater resources. So Soumya, Jimmy, and Akash, they are always participating in the training. No one else gets a chance to participate. Challenges, always taking a fixed subset can create a problem due to statistical heterogeneity because the data might not be representative of all of the client's data. So that creates a biased model. And it can also cause problems due to system heterogeneity and limited availability of clients. But statistical heterogeneity is a very important issue, and I think the paper addresses it very carefully. We're going to explain it later. So, as we have seen, that we have had some problems with the existing solution, and we work towards mitigating those. And we are gonna see what research questions are the authors form and what is our goal for the paper. So first goal of this paper is designing a practical incentive mechanism with partial client participation that ensures convergence to a globally optimal unbiased model. And the motivation we get from this statement is we have to explore clients' independent participation levels, and also we have to define the contribution of a client towards global training objective. And we need to take into account budget constraints, statistical heterogeneity for that. Then the second design question is designing efficient payment strategy by defining the contribution towards global training objective. And the authors propose two new concepts, bidirectional payment and intrinsic value for that. And we model the entire client server interaction as a two-stage sequential Stackelberg game. So Stackelberg game is a building block for this paper. I'm going to explain in very simple terms. So imagine you're playing some game, and this game has 50 characters, and these characters have to do some adventure. And for that adventure, you have an instructor. So the instructor says some instruction, and then 50 participants follow and go to the adventure. Say, go to forest, kill some dinosaur, or someone goes to forest, kill some tiger, whatever. Yeah. So that is so you always have a leader and a follower. And in this scenario, we design the leader as our server and the follower as our clients. For the proposed design, I think Jimmy can take over from here.
So with the previously introduced concepts, we can now explain the design proposed by this paper. So currently, the most popular optimization algorithm for federated learning is Fed average. However, this algorithm does not take partial participation into consideration. Just as Sumaya mentioned, this existing algorithm is aiming to incentivize the clients for full participation. So it simply weights the participants' update model by the amount of data it holds. And this could easily lead to a severe biased model due to data heterogeneity. So the paper proposed to incentivize all clients to join the federated learning with independent partial participation probabilities. So it introduced the arbitrary independent client participation level Q. With the newly introduced participation level, the paper proposed a new aggregation scheme. that is similar to the importance sampling, which is an approximation method that uses mathematical transformation to formulate the problem in a different way. And the paper utilized the newly introduced parameter Q to inversely reweight the participants update model gradient with the participation level Q. And one thing that is worth mentioning is that the simply inversely reweight the participants update model gradient does not guarantee an unbiased model. The proposed mechanism is able to achieve an unbiased aggregation scheme because the Q is independent among each other. So unlike most active sampling schemes with some of the sampling probabilities which are equals to 1, the sum of Qs is varying between 0 and n. And with the introduced participation level Q, there are also some corresponding modifications required for the client and the server in the proposed design. So let's start with the server. When the server is trying to minimize the loss of the global model, you need to take the participation level into consideration. Besides, the proposed design also allows the payment to be bidirectional, which is different from the traditional one that only allows server to pay clients for involving in the process. As for a client, the paper introduced 2 new models. The first one is the local cost model. The total cost of consists of resource consumption of client N involving in model computation, as well as the loss opportunity for joining other activities for reward. So since cost only increases as its participation level gets higher, the paper proposed to set the parameter tau to be larger than 1, which would capture a broad class of functions. And the paper claims that the theoretical result in this paper also hold for an arbitrary tau that is larger than 1. The other model the paper proposed is the intrinsic value model. For example, if a client could gain significant benefits from obtaining a powerful global model, it should have a high intrinsic value. When the client's intrinsic value is higher than a certain threshold, the clients may need to pay for the server for participation, and that is correspond to the previously mentioned bidirectional payment. And with the 2 models previously introduced, now we can formulate each client N's decision problem as maximizing its profit, which is the reward from participating minus its local cost and plus its intrinsic value. And with all the concepts and formulas we formed in the previous slides, now we can form our problem into a stakeholder game problem. So just as Jumia has mentioned, the 2-stage stakeholder game has server and client. Server decides the budget and pricing strategy P in stage 1 in our problem, and the clients will decide its participation level Q accordingly in stage 2. And how can we solve the 2-stage stakeholder game problem? The common solution concept is to find the Stackelberg equilibrium. And what is a Stackelberg equilibrium? It is a set of decisions satisfying certain conditions. And in our problem, in our case, it's to find the decisions that satisfy these 2 conditions. The first one is to find a QSE such that the profit of each client is maximized, and PSE such that the loss of global model is minimized within the budget that the server decides. And how can we obtain the SE? The common way to obtain SE is to use backward induction. And there are two steps in backward induction. The first one is to solve the client's decision-making problem, determine the participation level Q, given the server's pricing scheme P. Then we move back to stage one to determine the server's pricing strategy. However, the lack of analytical expression of the expected value of loss regarding to Q, which can help us characterize the impact of Q, is stopping us from getting a better result. Therefore, the paper conducted a new convergent analysis on the convergence and the relationship of Q. It made an extra assumption comparing to the previous researches. It assumes that for each client N with the bound GN, each client N has the expected square norm of its stochastic gradient is bounded by GN squared. And this is different from the existing works that have a single G for all the clients as its bound. And when clients have non-IID data distribution, the value of GN will be different. And so enabling each client to have different GN help us characterize the data heterogeneity in our convergence result, and therefore yields a more accurate pricing design. So in practice, we can estimate GN by letting the participating clients send back their actual gradient descent and compute the model updates to get the GN. And this helps us establish the relationship between the expected loss functions, clients' participation level, and their heterogeneous data.
Okay, so now coming to the experiment part. So in order to see how what is the performance of our proposed model, we are going to conduct an experiment. So for the experiment, we have a prototype which contains 40 Raspberry Pis acting as the client and one central server, which is a laptop. The server and the clients are interconnected by an enterprise-grade Wi-Fi router. These servers and clients communicate with each other using a TCP-based sockets. So for the experiment, we have three different setups. The first setup contains data from a synthetic data set. The second setup consists of data from MNIST dataset containing about 14,000 data samples. And in the third setup, the data is coming from EMNIST dataset, which contains about 35,000 data samples. For each of these setup, we have three parameters. They are the budget denoted by B, mean local cost denoted by C, and mean intrinsic value denoted by V. Here we can see the different values that we have set up for each of these parameters in each of these settings. Now we're gonna evaluate our proposed model with different pricing schemes. The first pricing scheme is going to be uniform pricing scheme, where it's the same price for each client. And the second pricing scheme is going to be the weighted pricing scheme, where clients' prices are dependent on their data size. And the third one is going to be the proposed pricing scheme that we have already introduced in the previous slides. Now I'm going to show you the observations and the results that we have seen. So coming to the third setup that we had done, which had data from the EMNIST dataset, we can see that our proposed model has minimized the global loss when it's using the proposed pricing scheme compared to the other pricing schemes. And for the same, our proposed model is able to achieve higher accuracy. Now, we will evaluate the performance of the parameters with our proposed model. So as the client mean intrinsic value increases, we see that our proposed model achieves lower global loss and higher test accuracy. This happens because as the intrinsic value increases, the clients are more interested and motivated to participate in the global model, and hence our global model is able to achieve better results. Coming to the next parameter, which is the mean local cost. So as the mean local cost decreases, we see that our proposed model performs better with minimized global loss and higher test accuracy. This happens because most of the clients won't be able to afford the large costs, which would prevent them from participating in the global model. So as we see that as the cost lowers, more participants are involved and we get better results. Finally, coming to the last parameter, that is the budget. As the budget increases, the performance of our model increases. We see minimized global loss and higher accuracy. This is obvious because more budget means more clients, and more clients means we can achieve better performance and better results. So to summarize, the paper proposes a new way for devices to join federated learning that gets better results without bias. We also see that we have found out how different device involvement and data affect the overall model. Devices that contribute more get rewarded more, and devices can also choose to pay to help improve the model they care about. Now, finally, we would like to share our opinions on the paper, what we have found interesting about it. So, one interesting fact that we see is missing from the paper is that they have not mentioned which machine learning algorithm is being used for the federated learning. Second is that they also have not mentioned the trade-off which is involved, which means that we don't know whether the server and clients are using the same machine learning algorithm or they're on different machine learning algorithm. Either of them would decide how our proposed model would perform for the better or worse. And finally, they do not mention how the server and client communication is secured. If the communication between server and clients are not secured, then there's a chance that anyone can tamper the results of our proposed model and significantly reduce the performance. So that's all we have. Thank you.